Okay, so page 11. Number one, we're asked to find the integral of 5x plus 4 to the fifth. Sorry, 5, yeah, to the fifth power. Anytime we see an integral problem, we should always ask ourselves, can we rely on just expanding and getting rid of the parentheses on our own? But we see that it's possible, but that anything higher than degree 2, we want to look for an easier, more efficient way. So then we know our option is now use substitution. So then we go ahead and start marking up what we're trying to do. So go ahead and underline the 5x plus 4. We're always targeting what's inside the parentheses. Okay, so we usually don't include the exponent as part of our u value. It's just what's inside the parentheses. And du over dx. Derivative. 5x becomes 5. If you want, you can put a divided by 1 as a, so you can kind of see how your cross multiplying is going to look like. So 5 dx is equal to du. Therefore, dx is equal to du over 5. We have our suitable substitutions ready. U to the fifth, du over 5. So our goal for this problem is trying to make it look like power rule. We want to make it look like this rule, because then we can apply power rule that we're used to. But we can pull that 5 out. That 5's in the denominator, so let's pull that 5 out as 1/5. So now we're ready to apply power rule. We don't have any x's left over. That's a good sign. It's okay to have leftover numbers. We just can't have any leftover variables or any leftover x's. If there's an x left over, we can't. We just can't find. Yeah, we can't find a creative way to find the antiderivative. We have to resolve it at this stage before we can move forward. But everything looks pretty good here. we can apply power rule. The 1/5 stays. U to the 6/6 plus c. As soon as you apply power rule, your integral and your dx or integral and du notation drops out. You're left with a plus c because there are no bounds. Then replace the u back in terms of x. You can put that 30 in the denominator, or you can pull that 30 out in front as 1/30. Either is fine. And if you're working ahead of me, that's great. You can also check your progress with the next page. I got the key on the next page. Okay, take a look at number 2. Go ahead and try this one. Ask yourself, can I expand my way through? If it's too hard or impossible to do, then use substitution as your next option. That 5 is a really high exponent for us to work with, so we don't want to try to expand this. So power rule is not a good option. Second option, use substitution. My independent variable is t, so instead of du over dx, we're doing du over dt. Hey, derivative is 3t squared. Go ahead and cross multiply. Get that dt by itself. Rewrite your problem, but only replace what we've underlined. Everything else we want to keep. The important thing is that the only variable we should have left are u's. The t should cancel out, and they do. It's not necessary for the numbers to cancel out as well, but it just so happens that the coefficients also go away. But if there are leftover coefficients, we can still move forward. We just have to make sure we keep track of them. It's a nice power rule, just like before. Now we can apply a power rule. Add 1 to the exponent divided by the new exponent. Remember, u is only a temporary variable. It's only to help us have an easier problem to solve, but we want to bring back our original variable. You can leave that 6 in the denominator. You can also pull that 6 out in front. Number 3, we can't rely on expansion. That square root is getting in the way. So we got to go through your substitution, but we don't see a set of parentheses. We can always rewrite radicals with the set of parentheses. That will give us an option for our u value. Cross multiply. Solve for dx. Make your substitution. No x's left over. That's a good sign. But we do have to keep track of that 4. That 4 is in the denominator, so let's make sure that we know where that is. I'm going to pull that out as 1/4. So it should be recognizable as power rule. Keep the 1/4, go through our power rule process, add 1 to the exponent, divided by the new exponent. Dividing by 3/2, the same thing as multiplying my numerator by 2/3. Okay, do some cleanup here. 2/12, the same thing as 1/6. And then bring back your original variable. Right, number 4, whenever you're ready. Number 4, too complicated, with too many terms in the denominator. We can't split up into individual fractions and rely on power rule. So we want to go through use substitution, but we would like to see a set of parentheses before we do that. So let's get that denominator to show us a set of parentheses. find a replacement for the x cubed minus 2, and then algebraically, we can also find a replacement for dx. Cross multiply. Make our substitutions. Again, we can't move forward until the x's go away, and they do, right? The x squared cancels out nicely. There's a 5/3 that we can push out in front. We want to do power rule, and everything is lining up pretty well, but there's one thing we have to be aware of here. We can only do power rule if the u is where? Where does the u variable have to be if we want to do power rule? Numerator, yeah. So we can't do power rule when that u is out of place. Okay, if we try to go through the add 1, divide by 1, it's going to mess up the numbers. It's not going to quite work out. So how would you rewrite this with that u in the numerator? It'll be u to the what? -1/5. So now we have that u in the right place to apply power rule. If you do power rule here, it's not going to get you the right numbers you're looking for. We need to have it up here with that -1/5. Now we can do power rule. 5/3 stays. Add 1 to the exponent. -1/5 plus 5/5 is 4/5. Dividing by 4/5, the same thing as multiplying by 5/4. Number 5, we do see a set of parentheses. So let's go after those. Pull the 1/2 in front. Now, we do have a rule for cosine, right? We know that antiderivative of cosine is a positive sign. And then we took the antiderivative, we dropped the integral notation, plus c shows up, and then we can replace the u back in terms of x. Okay, questions with 5? Okay, number 6, I do want to, well, first off, sine to the 10th of x times cosine x dx, we don't have one single rule that can handle this large of a problem, right? And we can't split up and say, okay, I'll do a rule for sine, I'll do a rule for cosine. These are being multiplied, so we have to go through a bit more complexity than just, we can't just find these separate rules and put a multiplication between it and do a plus c. Okay, it's there's more involvement than that. So your next thought is, okay, I got to go through use substitution. Okay, I see a set of parentheses, so why don't I just go after the x there? So when you go through use substitution, we never just want to say u is equal to x. Why is that? Why do we never just want to do a substitution with u equal to x? Right. I'm not changing the problem, right? I mean, I'm making it look I'm making the same problem look with a different variable. But the whole point of use substitution is you're trying to make your problem easier to work with, right? And if you just made a substitution with x with u, yes, you've turned it to be a different variable, but the overall look of the problem is still the same. So yeah, just be aware of that. Your u value is, if you want to go with u substitution, it's always more significant than just an x. Otherwise, there's no point in doing this process. So that's one thing to keep in mind, that it's not always just the parentheses, and it's never just the x. So we need something more significant than just the x. What if we can get a set of parentheses to show up? That 10 is a shorthand form, right? This is a shortcut way of writing the expression. We can rewrite it a different way. We can get that 10 outside a set of parentheses and make it this. All right, so now this feels a little bit more clear as to what our potential u value could be once we get that 10 to be outside a set of parentheses. So now there's our target. Okay, find the derivative, du dx. Sine becomes cosine. Cross multiply. Okay, let's make our substitutions. U to the 10th. We keep the cosine, and then dx gets replaced with du over cosine. Cosines cancel out. That's a good sign. And we're just left with a nice clean power rule problem. And number 7. Uh, this is nice. It's already showing us a set of parentheses, so we already know where to go, where to look for our u value. Derivative of cosine is negative sine. Cross multiply. Okay. Replace what you've underlined, but keep everything else in the problem the same. Sines go away, the x's go away, that's good. We want to do power rule, but again, what adjustment do we have to do with that u variable? Yeah, to the top. Careful, there's -1 that we got to keep track of in front, and we have to move that u up to the top, so we got to change that exponent to a -5. Now we can move forward with our power rule. Add 1 to the exponent. I'm going to bring that. Okay, so I'm already pretty much near the answer here. I'm going to do some cleanup. I'll make this 1/4. I'll pull the u down to the denominator as well. And then we'll bring back our original variable x. Okay, number 8. Too complicated for power rule to handle. As soon as there's more than one term in the denominator, you know that expansion power rule is out of the question. Let's get a set of parentheses to show up. Underline what's inside your parentheses, and then your dx. Those are the pieces we want to replace first. Let's multiply. No x's remains. That's a good sign. But again, the u variable is out of place. Let's clean up that coefficient in front first. And I also want to move that u up to the top before we do power rule. Okay, ready for power rule now? Flip that denominator fractions there. Okay, number 9. Two sets of parentheses. We can potentially let both of them be our u value because maybe this can head towards an integral rule that's available to us. We do have a rule for secant u tangent u. Right? So if you recall, we do have a rule that looks like this. Remember, first semester, secant's derivative is secant tangent, so therefore the antiderivative secant tangent is secant. So if we let both of these be our u value, maybe we can work towards this and hope that the 4 over x squared can kind of cancel out. So we'll target both of these as our u value, since this fits the potential rule that we could be moving towards. Now, I want to find the derivative for 5 over x. How would you find the derivative for that expression? What would you use? Yeah, and go through power rule, right? I mean, you could go through quotient rule, but I don't think it's worth the trouble to do it. I mean, you could, but it's just cumbersome, especially if you know that you can avoid it. Right? You know you can avoid quotient rule whenever one of your numerators or denominators is not a variable or is a constant. So there's no need for us to keep that x in the denominator. I mean, it's just easier to just bring it up and go through a power rule at this stage. Okay, so I'm going to rewrite that u value to be 5x to the negative 1 derivative, negative 5x to the negative 2. Now, I do want to cross multiply and do all that, but I just find it easier if I can resolve that negative exponent first, um, and then cross multiply and then solve for dx. Okay, so let me do this first. I've just rewritten it so that I can have an easier time with my exponent. Rather prefer not to work with negative exponents if I don't have to. I kind of had to at the beginning just to kind of get it ready for power rule. But once I get to my derivative, there's no need for me to hold on to that negative exponent. So I'm going to bring it down, cross multiply. Solve for dx. Replace what you've underlined, but keep everything else. We need the x's to go away, and we do see a path for that to happen, right? I got x squared in the numerator. I got x squared in the denominator. That's good. But there is some numeric coefficients that we have to keep track of. So let me pull those out in front. Now I should have a perfect rule for me to play with here. Secant tangent. Okay, replace the u back in terms of x. We have the antiderivative. Just have to make our final set of substitutions here. Okay, next one, number 10. Number 10 is already set up nicely for us. We already know where to look for our u value. And also, too many terms in the denominator. We can't split this up into individual fractions. No, there's no way to do power rule with this problem. X's cancel out. Pull the coefficients out in front, and then also move that u to the top. Before we do power rule. Okay, multiply, clean up, and then bring the u back down. Bring back your original variable. Okay, one last one here, number 11. What do you notice about number 11 here? Do we need use substitution for number 11? Okay, so there's only one term in the denominator. There's nothing that's complicated for us to expand out. So we can't do use substitution for this. It's not going to work. This is meant for power rule. So we should always, there's certain looks for power rule problems, right? Something is just raised to the second power. If the denominator only has one term, that's an indication, okay, I got to split up. I got to go through power rule. Even though I do see a set of parentheses, I'm not going to get things to work out with use substitution. Okay. So this is purely a power rule problem here. So just like how you were demonstrating on the quiz, this like similar to your quiz problem here. So you split up into individual fractions, subtract the exponents to bring the exponents up. Four minus 1/2, the same thing as 8/2 minus 1/2, which is 7/2. And then 3 minus 1/2 is 5/2. Now we have nice individual terms for us to do power rule. Add 1 to the exponents. Flip those fractions. Right, your homework is to complete pages 5 through 8 in your homework packet. I'll send out a reminder on Sunday, and I'll send you guys a link to the key as well. All right, can get you folks. We'll start our test review on Monday. We'll have Monday, Tuesday, Wednesday to review. We'll have tests on Thursday. I'll give back your quizzes on Monday.